Here are some examples of some objects that oscillate. A pendulum oscillates back and forth, and a spring can oscillate up and down. There is something special about these oscillations. When we plot their position as a function of time, we get a sinusoidal shape, and that is indicative of what's called simple harmonic motion. I've got my mass on a spring over my motion detector, and when I set it into oscillation, I can use the LoggerPro application to measure the distance that the mass is away from the sensor, and thus I can get a graph as a function of time of the position of the mass. Here I've set up my motion detector to detect the motion of this pendulum swing here. And when I start the lab quest, you can see the motion, the displacement of the pendulum. Simple harmonic motion is sinusoidal in nature. So how then can we model it with a mathematical equation? This type of motion that repeats itself is called periodic motion or harmonic motion. So if it's repeating itself over and over again, we have to choose a point for us to begin our analysis, or say where is time equals 0. So in our waveform, we have to pick a point. Scientists have chosen to use the maximum positive displacement as the starting point for our graph of displacement versus time. So that would be at this spot right here. Or at this spot, or at this spot, or at this spot. But we've chosen that to be our starting point. And when we model this kind of curve, this sinusoidal curve, we could choose sine or cosine to do that. But since we've chosen this spot as our starting point, we're going to use the cosine function that says the position as a function of time is equal to some number times the cosine. And we'll talk about what all these variables stand for in just a minute. The amplitude is the displacement from the center point. So if I draw a line down the middle, how far the pendulum or the spring oscillates from the middle point to one side and then the other, that distance is called the amplitude. So this distance right here is A, and this distance down here is also A, but in the negative direction. So that's this number here. And we're going to modulate that or vary this maximum amplitude using the cosine function. We know that the cosine of anything will be between 1 and negative 1. So that means our displacement in the x is going to vary from A times positive 1 down to A times negative 1. And that's what we see here. A times positive 1 all the way to A times negative 1, giving us a range of displacement in the x direction from positive A to negative A. In the center is our 0 displacement, and we're graphing as a function of time. So this form of the equation is the general form, A being a general term. If we're going to specifically talk about displacement of an oscillation, then we're going to use the letter x. X sub m stands for the maximum displacement, and that is the amplitude of our oscillation. So we're going to rewrite our equation as our displacement as a function of time is equal to the maximum displacement times the cosine of some number. And we're going to talk about what's inside of here coming up very soon. let's look at a specific example to help us understand what's going on. From now on, let's call one oscillation, let's call it a cycle. It's just easier to say, not such a mouthful. Okay, so in this example, we look at our graph and we see on our time axis, our time in seconds, right here is 1 second. So within this 1 second, I have repeating motion. I have an oscillation that repeats over and over and over again. That's what makes it harmonic. So we see here, it starts here and there's 1 cycle, then it begins to repeat 2 cycles, and it repeats 3, 4, 5, 6 cycles. So we have 6 cycles in 1 second. There is a vocabulary word to describe that. It is called the frequency of the oscillation. We abbreviate it with the letter F, and number of cycles in 1 second is the frequency. So for this example, we have 6 cycles in 1 second, so the frequency is 6 hertz. That is the name of the unit, just like the car rental company, 6 hertz, and it is abbreviated Hz. So F equals 6 hertz. And we notice that each cycle is of equal length. They're all the same length. So if there's 6 in 1 second, each one must be 1/6 of a second in length of time. So the period is 1/6 of a second. The frequency is 6 hertz. So that leads us to the relationship between frequency and period. They are reciprocals of one another. F equals 1 over T. Let's change our frequency to be 1 hertz so we can talk about what's inside the cosine function right here. So within this 1 cycle, I know that the cosine, this part of the equation, is varying from +1 to -1 to +1 again. And we know that for that to happen in the cosine function, this angle in radians inside the parentheses must vary from 0 to 2 pi radians. So that means for every oscillatory cycle, the angle that we take the cosine of goes from 0 to 2 pi. So for every cycle, we have 2 pi radians. So whatever the frequency is, we're going to multiply that by 2 pi to come up with what's called the angular frequency. This is the number of radians per second. Cycles per second is F, and since each cycle has 2 pi radians, if you multiply the number of cycles by 2 pi, you come up with the angular frequency, or the number of radians per second. Let's take a look at the units of that. Here we go. F is cycles per second, and we know there are 2 pi radians in every cycle. So when we multiply those together, 2 pi times F, and the units become radians per second. That is our angular frequency. Let's talk now about what it means to have this phase angle phi in the equation. If the phase angle phi is 0, then our equation for cosine would look like this. It would just be cosine omega t. And regardless of what the angular frequency is, at time t equals 0, this inside the parentheses would be 0, and we know the cosine of 0 is 1. So at time t equals 0 on our graph, here's our time axis, time t equals 0, the value of our cosine function is 1. That's how scientists have chosen to begin looking at oscillatory motion. Begin with positive x max as our starting point. But what if we wanted to look at a different location in the oscillation as our starting point? So in this graph here, I've drawn a different location on the cosine curve where time t equals 0 is. So if we used our equation, cosine omega t at time t equals 0, the cosine of 0 is still 1, and that is not the value we have here. So we have to adjust what's inside the parentheses so that when we take the cosine of it, for this example, we get 0. So we add what's called the phase angle. So now the cosine of omega t plus the phase angle, for this example, that has to equal 0. So we know for the cosine function, these are the values of radians that yield 0 for when you take the cosine of it. So at time t equals 0, if phi equals any one of these radian values, the cosine of that will be 0, and that satisfies this point on our graph. However, there's an additional requirement for phi. Phi also has to satisfy that the direction the curve is trending. Let me explain. So if this is my regular starting point with a phase of 0, there are 1, 2, 3, 4 locations shown here on this graph where the cosine is 0. But there's only 2 locations where the data is trending downward after the data point, as it is at our t equals 0 point in the graph we want to get the equation for. So this point trending up and this point trending up are not valid numbers for phi. Only this spot and this spot. So our possible phase angles for this graph right here is positive pi over 2 and negative 3 pi over 2. So the phase angle tells us how much we have shifted from this original starting point when the phase is 0 in the positive direction pi over 2, or in the negative direction negative 3 pi over 2. So when we write the equation, this is what it will look like. Let's test our understanding. Here we have 2 waves. I'll label them wave A and wave B. A is the blue, B is the red. And they are offset by some phase difference. We see that they have the same frequency, but they have different phase. Let's see if we can figure out what is the time between the maximum amplitudes of each wave. Right here are the 2 maximum amplitudes. How much time is between those 2 points? So first of all, we start off by looking at our time scale and see that our time scale is over 1 second of time. And within that 1 second of time, we have 2 cycles of oscillation. So here's the time I'm looking for. 2 cycles within 1 second means each cycle is half that time, or 0.5 seconds. So that is my period. The time I'm looking for is this delta t right here, and it's between the maximum amplitudes, but notice that it's also the time between the points of each wave that crosses the x-axis. In fact, if we take any 2 points that are in the same location on the wave, we can find the distance between those 2 points, and it will match this delta t. All right, so first, let's see if we can figure out what are the cosine equations that describe each of these 2 waves. So here we are for graph A. The amplitude is 10, so that's the number here. Cosine of omega is equal to 2 pi times the frequency. We could figure that out, but we don't really need to know that information to answer this question, so I've just left it as omega. But it is equal to 2 pi times the frequency. And the phase angle for wave A, that's the blue wave. So here's our normal starting point when the phase is 0, and I see it's a shift to this spot right here. So that's a shift of pi or negative pi, either one, but we'll go with pi. Okay? So that is my phase angle for wave A. For wave B, here's the normal starting point, and here's the actual starting point. So that's in the negative direction. I've changed my starting point by pi over 2. Or in the forward direction, I've changed it by positive 3 pi over 2. So I've decided to go with the positive number here. It doesn't really matter. So what is the phase difference? Well, the phase difference is the difference of these 2 phase angles. So that is pi over 2. So these are separated by pi over 2 radians. Question is, how much time is that? So pi over 2 is 1/4 of a full cycle of 2 pi. So 1/4 of the period then, 0.5 divided by 4, is 1/8 of a second. So this time right here, from here to here, is 0.125 seconds. Let's test our understanding a little more, go ahead and try it yourself. Plot this graph. Pause the video here, and then compare the graph you get to the correct graph that will pop up on the screen here in just a second. So pause the video here and try it. All right, let's try it the other way around. Here's a graph. Pause the video and see if you can come up with the equation for this graph. Then unpause and see the answer.